Right, so the previous video got cut short. Um, Now, boys, I sent that separately, so this one will be a third video on waves that you see on the YouTube channel. So if you have not watched two videos before this, you are skipping something. Do you understand? So now, which of the following statements about the third overtone of a vibrating air column of an open pipe is correct? So which of them is correct? It has, so the third overtone of an open pipe, third overtone of an open pipe. He said he has 4 nodes, he has 5 nodes, he has 3 antinodes, he has 4 antinodes. I think I will have to draw this so that we can understand what is happening of an open pipe, third overtone. Now, okay, let me not. Oh God, how am I going to do this? Okay, remember, if you're before you watch this YouTube videos, I hope you have completed the class I taught on sound on Telegram. Okay, you should have completed a class I taught on sound on Telegram so that you understand what I'm saying. Now, when I was trying to, in an open pipe, an open pipe starts with an antinode and ends with an antinode, right? Open ends, 2 ends are open. So antinode at the first, antinode at the second. So between the 2 antinodes, you must have a node. So that is the simplest form you can have, the basic form. You must have a node. The fundamental note has a node in between. Move to the first overtone, you have 2 nodes. Move to the second overtone, you have 3 nodes. And finally move to the third overtone, you have 4 nodes. So that's the answer. Let me see if I can get a diagram to show you what I mean. I don't think did I send a diagram. All the diagrams I have on Telegram are in videos. So to open the videos might be something else right now. Okay. Lecture ground. I'm not sure I sent a particular diagram for that open ends stuff. Not sure. It's only closed end I sent diagram for. But let me go to the textbook I was getting the pictures from. Yeah. So going up your way. This is new school physics textbook. So look at it here. Look at it here. So hope you can see. This is fundamental. You can see the point and place I'm touching. Just that's the one node that you're seeing there. Try to go away. That's just one node. At the top you have antinode, at the bottom you have node, antinode again. When in the middle you have one node. That's fundamental. First overtone you must have 2 nodes. Second overtone you have 3 nodes. Then the third overtone you have 4 nodes. Do you understand? So that's it. Alright, so let's go to our assignments. That was this question, right? Okay. Right, this is what we just saw. Next, the fourth overtone of a closed pipe is 900 hertz. Closed pipe, its fundamental frequency is. Remember that that closed pipe only takes the closed pipes only take odd number of overtones, odd number harmonics, right? Good. So the overtones are odd number multiples. Do you get? The fundamental frequency is F naught. The first overtone will now be 3 times F naught. The second 5 times. The third 7 times. I summarized it here. Let me go to my summary. I gave a summary on it. Remember the question talked about a closed pipe. So the question asked about a closed pipe. Where is my summary on closed pipes? So for closed pipes, this is what you have here from closed pipes. The fundamental, the formula is V over 4L, but we're not asked to find the fundamental. Okay, we're asked to find the fundamental, but not using that formula. So the first overtone is 3 times the fundamental. The second is 5 times. The third is 7 times. The fourth is 9 times. Just like that, odd numbers. Do you get? So which particular overtone was spoken about in the question? Let's go and check. Which particular overtone was spoken about? It was the fourth overtone. So the fourth overtone is 9 times. The first was 3 times, the second 5 times, the third 7 times, the fourth is 9 times. So let me go and write the formula out and then we solve. Math editor. So the ninth overtone, the ninth overtone is given as, sorry, the fourth, not ninth. The fourth overtone is 9 times our fundamental note, but then they gave us that fourth overtone that it is 900. So I have to find the fundamental note. So 9 times F naught. So divide both side by 9. So obviously your fundamental note will be 100 hertz. That's what your answer will be. So I hope that's clear. So moving on, 100 hertz is your answer, option B. Next question, the lowest note emitted by okay, so from here now we're talking about strings. Other ones has been on pipes, so from here will be about strings. The lowest note emitted by a stretched string has a frequency of 40 hertz. How many overtones are there between 40 hertz and 180 hertz? How many overtones are there? Now remember that your stretched string behaves like an open pipe. Your stretched string and open pipe, they have the same pattern of overtones and harmonics. That means, like, and what's that pattern? Every harmonic are possible. Unlike closed pipe, there is only odd numbers of harmonics that are there. For open pipe, every harmonic are possible. Same thing with strings. So now they're asking you for how many overtones are there between the 40 hertz and the 140 hertz. So these overtones, there will be whole number multiples of the what? Of the fundamental. For your string, if it was a closed pipe, there will just be odd number multiples. But since it's a string, it's every whole number from 2, starting from 2. So you will have 2 times 40 there, you will have 3 times 40, you will have 4 times 40, like that. Do you understand? So between 40 and 8 and 180, these are the numbers you will have. Let me go to my guy, SCAD. You will have, so 40 is the fundamental. Is you're not counting the fundamental as part of overtones. If it was harmonics, you will count fundamental, but overtones, you are not over must be over the fundamental. Do you understand? So the first one you have is 80, that's 40 times 2. Next one you have is 120, that's 40 times 3. Next one you have is 160. The next one you have is going to be 200. Now 200 is above 180. They said between 40 and 180, so it's 3 overtones you have: 80, 120 and 160. So 3 overtones, option B. Next one, a string is fastened tightly between two walls 24 centimeters apart. The wavelength of the second overtone, the wavelength, not even the frequency, the wavelength of the second overtone is, what's the wavelength of the second overtone? So for these guys now, this is the formula. The formula for the length is given as, for your fundamental, let's start with the fundamental first. The length is given as okay, wavelength over 2. Over 2. Okay, good. Yes. Then if you go to this is the fundamental note. Then if you go to the first overtone, you multiply by 2. This result you multiply by 2. Second one you multiply by 2. Third one, sorry, second one you multiply by 3. Third one you multiply by 4. So what did they ask us for? They asked us for second overtone. So we're going to multiply by what? 3. If it's first overtone, multiply by what? 2. Second overtone now multiplying by 3. So L is still going to be equal to um for the they gave us the length of the string already now, right? Give us the length of the string as what? Wavelength of the second. They give us the length of the string as 24. All right, so it will be equal to 3 uh times wavelength over 2. So this gave us the length of the string as 24. So this will basically be 24 equals to 3 over 2. You must cross multiply. You have 48. That's 24 times 2, 48 equal to 3 of the wavelength. Then you divide both sides by 3. So your wavelength in this case is going to be 12. That's what your wavelength will be. That's what your wavelength will be. 12. So that is the sorry. Sorry. Hold on. I think I'm solving it the wrong way. Our okay, yes. The wavelength is 12. Yes, that's correct. The way I solved it is correct. I was thinking of frequency. If it was frequency, that's not what I would have done at all. If it was frequency, that's not what I would have done. If it was frequency, this is the formula I would have used. Frequency, fundamental frequency is equal to fundamental frequency is equal to what's F? It's okay. If it was frequency, they would have talked about velocity. That's just the truth. That's V over 2L. If it was frequency, this is the formula, but they don't talk about velocity. Do you understand? So we cannot work with frequency. So the way I solved it, that was the correct way. So 12 is the answer there. So 12, option C. Question 3. If tension is maintained on a stretched string of length 0.6 meters, such that its fundamental frequency of 220 hertz is excited, I think exceeded or whatever, determine the velocity of the transverse wave in the string. If tension is maintained on a stretched string of length 0.7 meters such that fundamental frequency of 220 Hz is excited, determine the velocity of transverse wave in the string. This is something else, honestly speaking. Well, this is the formula normally we should use. What's that formula again? Okay, just this formula that is looking at our face here is the formula for frequency in a string, right? Frequency in a string, not just any frequency, fundamental. Let me write it. Fundamental. What did the question ask us to get against F? Always be clear what the question wants from you. The question asks us to determine velocity. And what did they give us? They gave us frequency and they gave us length. Okay, so we're just going to use this particular formula we are saying here. They give us frequency and they give us length. So we're just going to use this formula we're saying here. So it's not even complicated itself. Why was I even confused? So the frequency they gave us is 220 Hz. This formula is for fundamental frequency of a string. It also applies for fundamental frequency of an open pipe. Okay, so 220 Hz is the answer, is the frequency, equal to V over 2L. That's 2 times what is the 0.6. That's the length, 0.6. So our V will be, if you cross multiply, it will be 220 times 2 times 0.6. Take everything to your calculator. 220 times 2 times 0.6, 264. So 264 is the answer. That's velocity. Yeah. Option B. A transverse wave is applied to a string whose mass per unit length is this. Okay, if the string is under a tension 12 Newton, the speed of the propagation of the wave is. Now let me go and show you the formula I'm using. Discard. Hope I saved it. I should have. Yes, this is it here, over here. Edit. So this, what you are seeing here, is the formula. So this V equal to square root of T over M is the formula for velocity, and that M, we call it mass per unit length. mass per unit length. Okay, good. Now that's the formula for the velocity. What did the question ask us to get? The question asked us to get the speed of propagation. So they've given us the tension, they've given us the mass per unit length, that capital M. So you just to apply that formula, okay? So applying this formula, which is V equal to square root of T over M. That's what we're applying. So T from the question is 12 and M from the question is, let me check, 3 times 10 to the power of minus 2. Alright, so what do we do? Since this 10 to the power of minus 2 is at the denominator, having a minus sign, it can come up and have a positive sign, and then you also do 12 divided by 3 having 4. So basically there will be nothing again in the denominator. You do 12 divided by 3, it becomes 4. That 10 to the power of minus 2, you take it up, it becomes 10 to the power of 2. Do you understand? So when you take the square root of this kind of thing, take the square root of 4. Square root of 4 is 2. And then when you take square root of indices, you just need to half the power. So the power is 2. You divide the power by 2 because we're taking square roots. Square root means to divide the power by 2, okay? So 2 divided by 2 is 1. So this times 10 to the power of 1. 10 to the power of 1 is just 10. So that's 2 times 10, which is 20. So 20 meters per second is your answer. Option B. Which of the following is a stringed instrument? Piano. Piano is a stringed instrument. Next one. A string is stretched between 2 points 50 centimeters apart. Let me check that thing again. Yes, piano is a string instrument there. A string is stretched between 2 points. Okay. So that you know the rest except saxophone. Okay. Oh, all of them are. Flute is an organ that has to do with air. Um, Piano is string. Trumpet is organ. Flute is organ. Drum is percussion, the one you have to strike. Saxophone as well is organ as well. Saxophone is different from xylophone. Xylophone is just like drum, you have to beat it. Alright, so let's move on. A string is stretched between 2 points 50 centimeters apart. It is then plucked at its center, and the velocity of the wave produced is 300 meters per second. So when you pluck a string at the center, you are producing fundamental notes. Plucking at the center produces fundamental notes. Take note of that. Okay, I did not mention that in class. I mentioned it here. So it's to your advantage that you are watching the video. So that's fundamental notes. And what's fundamental note of a string? The frequency. Is it not F equal to um F equal to V over 2L? That's it. So they're asking you to calculate the number of vibrations made by the string in 1 second. Big grammar. That's frequency they're asking you to get. What's the meaning of frequency? Number of vibrations per second. That's what they just asked you to get. They say calculate the number of vibrations made in the string in 1 second. All that long sentence is simply calculates the frequency. That's the meaning of frequency. Do you get? So they're asking for the fundamental frequency, which you said is V over 2L, right? So we solve. Okay, so let me save this for exiting. Alright, V over 2L. Yeah. F equal to V over 2L. So V in this case they gave us as, is it 300? Yes, 300. And L is 50 centimeters, so change it to meters, that's 0.5. So this is 300 over 2 times 0.5. 0.5 times 2 is 1, so this is 300 over 1. Our answer will be 300. So that's the fundamental frequency, 300. So B is the answer. Alright, question 18. If they had asked you to calculate the time taken for making a certain amount, that one is period. Do you get? But let's leave that aside. Question 18. The quality of a note produced by a vibrating string is determined by, remember that sound has 3 characteristics: loudness, pitch, and quality. Loudness depends on amplitude, it depends on volume of air in vibration, depends on surface area of vibrating surface. But then pitch depends on frequency. But then quality, which we also call timbre, depends on these overtones and harmonics. So option D is the answer. Question 20. A string of length 1.0 meter vibrates in 10 loops. 10 loops. So that's between the two ends that are fixed. There are 10 waves, like there are 10 loops. Let me show you what I mean by a loop. Let me show you what I mean by a loop. I hope this is the textbook. Where is that string? Basically, from one node to another node is a loop. Where is my string now? So, in this particular one, you have two loops. These two loops, okay? In this, where else? In this one, just one loop you have. This one is two loops. So this one is three loops. Yeah, you have three loops. So they said it has 10 loops. They're giving us that 10 loops for us to use to get wavelength. Okay, that's why they're giving us that amount of loops. Look at this one that had one loop. This one loop was half a wavelength. One loop equal to half wavelength. One loop equal to half wavelength. So if one loop is half wavelength, basically means that 10 loops is 5 wavelengths. Did you get? 10 loops is 5 wavelengths. So inside that string, you have 5 wavelengths. So the length of the string divided by 5 is 1 wavelength. When you have that 10 loops, inside that length of the whole string, there are 5 wavelengths in it, meaning that you take the length of the string, divide it into 5 places. Each of those 5 places is a wavelength. Did you understand? So that's why they gave us the amount of loops. So a string of 1 meter vibrates in 10 loops. So that means there are 5 wavelengths in it, meaning that when we divide this length of the string into 5, the answer we get is a wavelength. So let's do that now. You have 1 meter, which is 100 centimeters. If you divide it into 5, you have 20 centimeters. That's 0.2 meters. So 0.2 meters is the wavelength. Let's write that down. Are you seeing the way I'm reasoning the questions? Is how your mind should be running when answering these kind of questions. So sorry, our wavelength is equal to 1 meter divided by 1 meter divided by 5, which is 0.2 meters. So 0.2 meters is our wavelength. Let's keep that down. Let's continue reading. If the total mass of the string is, they give us that value, and the tension in it is 10 newton, calculate the frequency of the vibration. Calculate the frequency of the vibration. So there's a formula. I recently opened it. I'm going to open it and come back to this page again. This is the formula. It is one. I even sent it to the when I was teaching. 1 over 2L square root of T over M over M, where M is mass per unit length. M is not mass. M is mass per unit length. So if they don't give you mass per unit length and they give you mass and then use that mass in this formula, you are wrong. Okay, so what you have to do is you have to get the mass per unit length. How do you get it? M is equal to M over length. That's what did they give us as the length, as the mass. This 1 times 10 to the power of minus 3. That's what they give us as the mass, and the length is 1 meter. So 1 times 10 to the power of minus 3 divided by 1, it still gets the same thing, 1 times 10 to the power of minus 3. So now we are permitted to use this 1 times 10 to the power of minus 3 because that is the mass per unit length. Do you understand? So that is the formula we're using for our fundamental frequency of a string. All right, copy this, come to the next line and paste. All right, so the length is 1 meter, so times 1. Sorry. What did they ask me to find, sir? Calculate the frequency of the vibration. So calculate the frequency of the vibration. Okay. Oh, yes. They did not say you should calculate the fundamental frequency. If it was fundamental frequency, you have only one loop, but this guy had 10 loops, so this is not fundamental frequency. It's not fundamental frequency. It's not fundamental frequency. Now, this formula is for fundamental frequency. So I'm going to edit the formula now to just formula for velocity first of all. So now let's get the formula for velocity. This is the formula for velocity of a wave in string, of a wave in a string instrument. That's the formula. So let's get this. You will have T is, they give us the tension as what, sir? The tension is 10 newtons. So that's 10 over 1 times 10 to the power of minus 3. So duplicate this 10 to the power, that one is useless, just that 10 to the power minus 3, carry it and come up, right? So you have 10 as a numerator times 10 to the power of 3, which will give us 10 to the power of 4, right? Give us 10 to the power of 4. So V is equal to square root of 10 to the power of 4. Then 10, if you take square root of 10 to the power of 4, just like I explained before, is to half the power. So this is V being equal to 10 to the power of 2. That's 100. 100 is the velocity. Now, remember that velocity is equal to frequency times what? Wavelength. Thank God we have gotten the wavelength already as 0.2 from the beginning here. 0.2 was the wavelength. And now is the frequency we need to get. This frequency now is not fundamental frequency. Okay, so V, which is 100, is equal to F times what's our wavelength? 0.2. Divide both side by 0.2. You have F being equal to 100 over 0.2, which will give us 500. So 500 hertz is the answer. Option E. So let's move on. Under constant tension and constant mass per unit length, the note produced by a plucked string is 500 hertz when the length of the string is 0.90. At what length is the frequency? 150 hertz. So this time around, they said the tension is constant, the mass per unit length is constant, but did not tell us that the length is constant. So this, I wrote a formula before that I had to erase. Let me save this solution and open a new guy. So F is equal to okay. So okay, let me just use this formula. F is equal to velocity, F naught rather. Sorry, hold on. Let me look at the question again. Okay, they give us the length, constant tension, constant mass per unit length. That means the velocity will be constant. Constant tension, constant mass per unit length. That means the velocity will be constant. Remember that velocity is square root of tension over mass per unit length. So if the two things that velocity depends on are constant, it means that the velocity itself will be constant, right? Good. Now, okay. Okay. So, all right. Now, F for a string, remember that F is equal to V over 2L. Good. Now, V is constant. What is changing is L and F. In the first scenario, in the first case scenario, our F was what? What was our F? Our F was 500. 500 is equal to, we don't know what V is, but we know that the length in the first case scenario was 0.90. That's 2 times 0.90. 9. So you can find V for that first case scenario. V cross multiply, you have 500 times 2 times 0.9. Okay, so at the end that will be 900. So 900 meter per second was the velocity in the first case scenario. So the velocity will remain the same in the second case scenario. The velocity remain the same. Now in the second case scenario, we are asked to get the length. So in the second case scenario, we are still using the same formula again. F equal to V over 2L. So the V is still going to be that 900. The frequency in this case they gave us as 150. So this will be 150 being equal to 900 over 2L. So when you cross multiply, you have 150 times 2L being equal to 900. 150 times 2 is 300. So 300L equal to 900. Divide both side by 300. You have L being equal to 3. So 3 meters is the answer. So option A is the correct answer. Next question. Okay, this is second to the last question now. Two strings of the same length and under the same tension gives notes of frequencies in the ratio 4 to 1. In the frequency 4 to 1. The masses of the strings are in the corresponding ratio of. Okay, so the lengths are the same, tension are the same. What is not the same is the mass. Length the same, tension the same. What is not the same is the mass. Their frequencies are also not the same. So let's look at this now. So you know that F is equal to 1 over 2L being equal to, wavelength over, sorry for the noise. Alright, so now we're going to, and you know M itself, this M that you're seeing here is mass per unit length, right? So its value, I'm going to change it and put M over L. Yes, I'm going to change it and put M over L. Good. Now we're working with two case scenarios. So we're going to be having F1, we're going to be having, they tell us that the lengths are the same. So they said the same length and the same tension. So we'll not have L1, we'll not have T1. So let's just leave L and T like that. We're going to work with M1 as well. We're going to be working with M1 as well. So we're going to be working with that. And then we'll also have the values for F2. So F2 as well. We also have its corresponding M2. The question asks us to get the ratio of the masses. That's why we have M1 and M2. They already gave us the ratio of the frequencies. So they're telling us that when we take this ratio of F1 to F2, we have to get an answer which is equal to 4 to 1. Okay, so I have to be working on the road to solve this now. Hold on, I have to leave where I am now because it's closing. Okay, just give me some minutes, then I return. You can't pause the video, that's just the issue. The video can't pause. Alright, so I'm working, so just find a place to stay and just many two questions, then I'll be done. So the ratio of the frequencies of F1 and F2 is 4 to 1. That means if I take the ratio of these their formulas, I should get the same answer. Do you understand? So I'm just going to take the ratio of their formulas. Okay. So ratio. Ratio. Hold on, I'm trying to. Hmm? Right. Ratio. Alright, the other guy. So on both sides of this ratio now, we can cancel out this 1 over 2L. You can cancel out 1 over 2L because they occur on both sides. You can also cancel out T because it occurs on both sides. Then you see that over L that is inside that square root, you can also cancel it. Anything L, T, we can cancel them out because they are the same on both sides. Do you understand? So what will be left? Nothing will be outside there, outside the square root. Nothing will be outside the square root side. Okay, at the numerator, only 1 will be there because when we cancel out T on both sides, only 1 will be left. Then this over L as well will be cancelled out because it's common on both sides. I hope you know the reason why I'm cancelling these things out, because they are common on both sides. So this is what we have. So this ratio is supposed to be equal to this ratio is supposed to be equal to 4 to 1, right? It's 4 to 1. Assignment. Okay, it's 4 to 1. Alright, ratio is 4 to 1. So 4 ratio 1. Good. So I can also cancel out square root. Since square root is common on both sides, I can also cancel out that square root on both sides. So square root is gone there, square root is gone there. Do you get? Good. Now removing ratios, put it as fractions. Moving ratios, put it as fractions. 4 over 1. So this is, I can remove this fraction and now put even division this time around. Yes, and then 4 divided by 1 is 4. Okay, now you know that when you're dealing with division, you can change division to multiplication, and after you change division to multiplication, you inverse what you have there. So instead of having 1 over m2, I will have m2, and then when I do that, I will have m2 over m1. m2 over m1. So what did they ask me to get? Said the masses of the string are in the corresponding ratio of. So since we did f1 ratio f2, we should also get m1 ratio m2. We worked with f1 ratio f2. Look at it. We worked with f1 ratio f2. So our answer should be m1 ratio m2. But what I have here right now is m2 ratio m1 because m2 is up. So what do? I simply take the inverse, right? Take the inverse. So m1 will be at the top and m2 will be at the bottom. And then if I'm taking the inverse on that side, I also take the inverse here. So here becomes 1 over 4. So 1 over 4 or 1 ratio 4 is the answer. 1 ratio 4, option C. Next question. The lowest note emitted by a stretched string has a frequency of 40 Hz. How many overtones are there between 40 and 150? We solved something like this before. You just to multiply. Stretched string, every whole number multiple are there. Unlike closed pipe, there's only odd numbers. So 40 times 2, we start with times 2, 80 is there, times 3, 120 is there, times 4, you get 160, 160 is not there. So it's only 80 and 120. So there are only 2 notes that are there. There are only 2 overtones that are there. So option B is the correct answer there.